We're going to have a look at the first algebra theorem of the semester, and specifically we are going to prove that integer division always exists and it is unique. Now, namely, we claim that for every integer ab there exists precisely one per qr such that A is equal to BQ plus R, and R is non-negative and is smaller than B in absolute value. Very well. As I have mentioned before, this effectively tells us integer division exists and it is unique. So let's begin the proof by demonstrating the existence of such a decomposition, really. Alright, so suppose we choose the largest possible Q Q such that BQ is smaller or equal to A. Such a Q surely exists, and we can select the largest. Then we define the remainder as A minus BQ. And by construction then, the decomposition exists. So this was quite easy. Let's have a look at the uniqueness. It is slightly more complicated, but not by much. Alright, so let us assume that there are two such pairs QR. So assume there exist pairs Q1 R1 and Q2 R2 such that they both satisfy our conditions. That is, A is equal to B times Q1 plus R1 is equal to B times Q2 plus R2. And of course, it holds that R1, R2 is smaller or equal to B in absolute value. Well, quite easily, we can transform this equality into the following form. Simply by rearranging the terms, we obtain that B times Q1 minus Q2 is equal to R2 minus R1. Well, we are dealing with integers only, and this means that B as an integer is equal to R2 less R1 over Q1 less Q2. Well, but this then means that B must divide R2 less R1, otherwise it would not be an integer. So we deduce that B divides R2 less R1. But at the same time, we know that R2 less R1 is smaller or equal to B in absolute value. But naturally, since both R2 and R1 are positive numbers, and both individually are smaller than B in absolute value, we obtain this equality. But of course, this contradicts unless R2 is equal to R1 and the whole term is 0, the equation up here. Because if R2 and R1 are smaller than B in absolute value, then we have something small being equal to something large multiplied by something A that is positive and B that is at minimum 1. So it follows from this that R2 minus R1 is 0, and thus R2 is indeed equal to R1, and thus Q1 is equal to Q2, and we have thus proven the uniqueness of the integer division. And that's precisely what we wanted to do.